everybody. I know it is 4 o'clock on the last day of the workshop, so thanks for being here. I'm Emma Brunskill. This is work being done with a lot of the fantastic students and collaborators that I have. So I just want to start off with a little bit of motivation for the class of problems I'm going to talk about. I direct the Stanford Artificial Intelligence for Human Impact Lab, and so I think a lot about how do we use reinforcement learning to tackle problems that arise in things like education and healthcare, and then I think about the foundational questions for RL that come up when we try to do this. So in particular, I think we've seen some incredible successes led by some of the people in this room on things like Atari games and robots. But robots and Atari games are a little bit different than people in many ways, but I'm going to highlight 2 ways which I think they're particularly different. So one is that in Atari games, it requires computation in order for us to learn, but it's fairly cheap. So it might require millions of training episodes, and that does burn up computational power, but nobody is harmed if our agent fails to win at Montezuma's Revenge really millions of times. Whereas in the things that I develop, like intelligent tutoring systems, if we launch them on the world and they fail to teach 2 million students fractions, that seems really bad. So the scenarios that I think about tend to be pretty high stakes, because I think about students or patients or customers or other scenarios like that, and those are cases where sort of the mistakes we're making matter. The second is that in other cases where it's not quite so cheap to try things out, things like robots, we often still have pretty good models of how things work. We have pretty good physics simulators. They're not perfect. There's a lot of really exciting work going on right now on sort of the sim-to-real problem. But nevertheless, they're pretty good. And I think they're much, much better than how well we can mimic people. So people's learning, people's physiology is very difficult for us to model. And so we're in this scenario where we have sort of high stakes settings, and we also don't have good simulators of how people act or how they behave. And so that motivates my interest in what I might call bounded exploration. And I'm going to use the word bounded in many ways in this talk. I'm going to use it to refer to some of our theoretical work. I'm going to use it to refer to the fact that we may want to be optimistic and bounded in the amount of exploration we do. And I'm also going to use it to refer to the fact that we may have bounded amounts of computation. And before we get started, I want to talk a little bit about how we can evaluate whether an algorithm is good at all. So what are the criteria we want for success of our algorithms? So Ian led us off, and we've had a number of different people, including Chaba today and Marta, et cetera, talking about what might be the criteria for success, and typically referring to some existing measures. So probably everybody here is familiar with this, but let's think about the episodic reinforcement learning setting, where we just get to measure how much reward we obtain on each episode. So here, the red bars are how much reward our agent got or our algorithm got. And you can see maybe at the beginning it did okay, then it actually did worse for the next couple episodes, and then it started to do really pretty well. And so if we look at something like a regret bound, and this has been defined before, we're going to compare how well our algorithm is doing to what would be the optimal return in each of those episodes, the optimal average return. And then we can look at these blue bars, which is essentially how far are we from optimal. And so our regret is just going to be the sum of those blue bars. How far are we from optimal, and summing that up over time. And a lot of existing algorithms create bounds on the expected regret. So expected regret has a lot of really nice properties, but it also has some shortcomings. So the first is that expected regret only talks about in expectation. So that means on average, when you run this algorithm, this is what will occur. It doesn't guarantee with high probability this will occur. And there's also no information on the severity of mistakes. So you could have a particular regret bound by having a few really bad episodes. For example, in healthcare, you could have really, really bad outcomes for those patients. Or everybody could have a headache. So there are these different types of scenarios that both would look equivalent under this performance metric. And so that it would be nice for us to be able to distinguish between the performance of algorithms under each of these 2 cases. So a second framework is one where we can tolerate near optimal behavior. So again, I've kept around those bars that are showing us the difference between how well our algorithm did and how well it could have done. And what I'm going to argue here is that if it's below epsilon, then we care about it. So if we're not near an optimal decision, that's bad. But if it's near an optimal decision, we're going to color it blue and say that's tolerable. So maybe we don't need to be optimal, maybe we just need to be near optimal. So maybe slight headaches are okay, and that's fine, but severe side effects is not tolerable. So these are often known as PAC bounds, probably approximately correct, and these typically requires input an epsilon and a delta. And the type of guarantees they give is they say on all but n time steps, we're going to make a decision that is near optimal, epsilon close to optimal, with high probability, probability 1 minus delta. And so these are nice. They're sort of giving us a bound on the number of bad mistakes that we might make, but they also have some limitations. So the first is that whenever we're making those mistakes, we again don't know if it's really, really bad or just slightly bad, slightly worse than epsilon suboptimal. So is it the case that someone just had, a particularly bad headache, not just a slightly bad headache, or is it the case that they had to check into hospital? The second one that might be also quite concerning is that the algorithm might not converge to the optimal policy. So when I talked to Tom Mitchell, who I think of as sort of being one of the founders of machine learning, he argues that a machine learning discipline is concerned with algorithms which improve with data they learn. And one of the strange things in some of these PAC-RL algorithms is that they don't guarantee that with an infinite amount of data, you will converge to the optimal policy. You might stop learning at some point. And that also seems undesirable, and certainly isn't something we do in practice. We continue to have our algorithm learn, and yet some of these bounds through the sort of technical techniques require that we stop learning. And then the final hard thing is that we might not know how close to optimal is reasonable. What should that epsilon be? It's sort of unclear. We might know how to set that in advance. So when we were thinking about this, we also were curious, well, what is the relationship between these different types of frameworks for evaluating how good an RL algorithm is? And when my student Chris Dan and our collaborator Tor Lattimore we all started digging into this, we realized that there was a lot of incompatibility between some of these different guarantees, and in particular, that it was not possible to get an algorithm that was both probably approximately correct and obtained expected regret bounds. So that there wasn't, that we could have incompatibilities between these, and then other things where it doesn't directly imply, but it might be possible to achieve both. So it seemed clear that we might want to be able to sort of obtain things that are regret-like or PAC-like. There were direct things saying you could not get expected regret and PAC results at the same time, but maybe while we didn't have some of these other ones, maybe there'd be new frameworks which would allow us to inherit the benefits of these and avoid the limitations. So to do that, we introduced what we call delta uniform PAC bounds, or uniform PAC. And the idea is simply that for all epsilon, we should be able to tell you the number of times we might make mistakes that are worse than epsilon. So this allows us to avoid a lot of the shortcomings that we were just discussing. So it's going to now say, if you want to be really close to optimal, you only want that mild headache. We can tell you how many times that you might not make that mild headache. If you are happy to tolerate a really big error, you might need way less data. And so we can get a bound on all epsilon simultaneously. So the nice thing about this is it immediately implies that you have to converge to the optimal policy over time, because this has to hold for all epsilon. It immediately gives you a PAC guarantee for any epsilon, and it gives you regret bounds that are tight in terms of their dependence on the time step. So the nice thing about this framework is then it gives you stuff that immediately implies both PAC and uniform high probability of regret bounds. And we think that it's a much stronger notion of the type of performance we want for at least our theoretical algorithms. Okay, so that just sort of tries to argue what, at least on the theoretical side, what might we want to aim for? And now I'm going to argue to you that it's possible to do this. And I'm going to think a lot in this talk about how should we be computing a value function. So I'm going to be talking a lot about model-based reinforcement learning, and how should we compute a value function in order to get fast learning. So let's think about this first for the tabular setting. So we've heard about this before. A lot of reinforcement learning algorithms do this principle of optimism in the face of uncertainty. And this slide was made by my graduate student, and one of his primary concerns is figuring out where free food is. So he has this example where, behind some doors there is it's kind of not very good free food like cookies. And beside other doors is the faculty lunch leftovers, which are awesome. And you want to figure out where these are. And we know that these sort of problems where you might have sparse high reward and misleading other rewards are ones which you might require strategic exploration. And optimism under uncertainty does this, because you imagine that all of the world is fabulous, and so then you try to explore everything. It kind of forces coverage. And so by doing this, then you can start to learn a good policy, and you can do so fairly strategically. So when we were thinking about how to achieve these type of guarantees, we introduced this new algorithm called UBEV. And it follows sort of a standard model-based reinforcement learning approach, which is given some data, we're going to compute a Markov decision process model. And in this case, we're going to just compute a maximum likelihood estimate model. Remember, we're in the tabular setting right now, so that's completely feasible. And then once we have that model, we do MDP planning. And this is where we have to think a bit carefully about how are we going to do that MDP planning. And the innovation that we had here was that rather than add on sort of a reward bonus that's based on our predictive models about how well we can predict the reward or predict the transition model, we're going to do a tighter reward bonus by looking at a combination of the dynamics and the value function. And the reason that this is important is because we don't actually care about our predictive models within their own right. We care about them in terms of how well we know the value function. And so we can get tighter confidence estimates and tighter reward bonuses. And why do we want tighter reward bonuses? Well, the idea is that you want to be optimistic, but just optimistic enough. Because if you're too optimistic, you're going to spend too much time exploring. So that's why this is useful. And then once you do that and do the planning, then you're going to take an action that maximizes this optimistic value function. And the nice thing about this is that this algorithm, which is pretty similar to a lot of optimism approaches, but uses this tighter reward bonus, is uniform pack. So it satisfies these guarantees, and it has strong regret bounds, and it also has strong pack bounds. I just want to mention that this is closely related to some nice work that came out of DeepMind last summer in ICML that was developed in parallel. They have nice aspects that are stronger than our results. They have tight bounds on the expected regret, which is really cool. They, in terms of limitations or sort of strengths of our approach, we also introduced this new measure of how efficient an RL algorithm is, called pack uniform. And we also show how you can avoid union bounding by taking the sort of law of iterated logarithms in order to get much tighter confidence intervals. And that ends up helping us a lot when we want to make these pack uniform guarantees. Okay, so it's possible for us to define new ways of thinking about reinforcement learning algorithms being good. It's possible for us to achieve these results, at least in sort of tabular domains. But there's a number of problems with tabular MDPs, as many of you know. And there's sort of problems for them in two ways. So tabular stochastic episodic MDPs are extremely generic. And in some ways, they're way too generic. So they ignore all sorts of problem-dependent structure. You might have a domain where the dynamics is deterministic, which often comes up in controls problems, or you might have other structure that you want to leverage. So one focus in my lab right now is thinking about how do we get algorithms with better problem-dependent bounds. And what do I mean and why do I think this is important? Well, first of all, I think we see so much excitement about AI right now, and we see a lot of people who want to use AI and RL that are not PhDs in reinforcement learning. And if they're going to be able to use these algorithms, we want them not to have to know the distinctions between Bandit and RL or POMDP learning, and we want them to be able to kind of off the shelf be able to grab a nice technique and just use it. But the problem is that the existing analysis is fairly limited for these types of settings, and we know some hardness results. So for example, we know that in general, an MDP is strictly harder to learn than a Bandit. And so if you pick the wrong framework and you actually live sort of in a simpler class, you can suffer. So the questions that we started looking at in this case was, do existing algorithms already have sort of strong problem-dependent guarantees and we just don't have the analysis for them? Or is that lacking and do we actually need new algorithms? And so the first case we started looking at for this was thinking about, let's say you have an RL algorithm that sort of models the world as an MDP, but you actually are living in a Bandit. And as an example of where this might occur, so imagine that you're searching on Amazon, and in reality the world is a POMDP, like you're searching on Amazon because you have an intent about buying all the things you need for a vacation. But it might be that you really need to model that partially observable intent, or maybe I need to model the fact that the suggestions I make on one page influence my behavior on the next, or maybe it's just a bandit and whatever product selections you give to me today or don't affect anything I need for tomorrow. So it's often unclear whether something's a bandit or an RL problem, and it's important in terms of the data we need. And these theoretical bounds differ significantly, as I said. And so one of the things we found that was exciting and surprising is that a minor variant of the algorithm I just presented automatically matches the best regret bound in the higher order terms if it's executed on a bandit. So it both has very good guarantees for the RL setting, but if it turns out that your problem is really a tabular bandit, then you're going to do almost as well as if you used a tabular bandit algorithm instead. So this is joint work that we presented this week, and I think it's encouraging of thinking about how can we develop better problem-dependent bounds and settings. Okay, so I just talked about a case where the real world is easier than sort of tabular, stochastic, episodic MDPs. But in other ways, the real world is much more complex. So we've heard a number of nice examples thinking about how do we tackle much richer, harder problems than thinking about grid worlds or bandits. And in particular, often we have enormous state spaces. So the final thing that I wanted to talk about today is, again, thinking about model-based reinforcement learning and how do we compute a value function that's good for reinforcement learning in these sort of enormous domains, where both things are enormous, but we need to do computation in a scalable way. Maybe because we're doing real-time planning or because we have other types of constraints. So this is Pitfall, and I would argue this is perhaps the most challenging Atari game. Montezuma's, it might be this or Montezuma's, both of them are very hard. I'll do a quick poll. Who here is familiar with sort of Pitfall? So a number of people, but not everybody. I wasn't either before around a year or two ago. Pitfall is a game with, I think, about 255 level or 255 rooms. Your agent can navigate, there's over sort of logs. It tries to get rewards, and rewards are extremely sparse. And so a lot of the standard deep reinforcement learning algorithms just learn to cower in place because you don't experience any of those positive rewards for so long, and the world all just looks bad because you're trying to go over logs and they're tripping you up, that often the agents just learn to kind of stay in place or do a policy that gives them zero reward, and that's actually better than negative reward. But we were really inspired about thinking of, well, how could we kind of tackle these really large domains and do it efficiently? And this is something where we already have an existence proof that people do this. People do this and they do it easily. And Pitfall is still a pretty hard game, but they don't spend 200 million time steps to try to learn it. People can do very well on this game. And there's been a couple conjectures for why. So there's some really nice work by Michael Littman's group in 2008, looking at if you extracted objects and did object-oriented reinforcement learning, how efficient one could be. And then there's also some really nice work from Josh Tenenbaum and Sam Gershman and others, looking at how people play Atari games or looking at sort of similar types of games as Atari, and arguing that people seem to be doing something like object-oriented, sort of strategic model-based exploration, where people are modeling the world in terms of objects, and then they're building theories or models of how those objects interact. And so we were inspired by this and thought, well, could we do this in the Pitfall setting, and in general for Atari? And I'll just say here, so we're going to move to an object-oriented representation. And the reason why I think that's reasonable is I think that computer vision is advanced enough that we can basically assume that it's reasonable to extract objects. So here we built a specific object detector, but I think that if these were realistic scenes, we probably could just extract objects. They're not, but I think we're very close to assuming vision can solve that for us. So compared to some of this prior work, there were sort of two key insights that we had that sort of contributed to our ideas. The first was how we're going to model the world is a little bit subtle. So what we're going to make an assumption is that there's some model of the world that makes the world look deterministic. Now, of course, in Atari, that's actually exactly true for the standard Atari games. It wouldn't be true in everywhere. But it's clear that that's sort of a reasonable approximation for a lot of how people think about doing planning and learning. And so we thought we would build that in to start. So the idea in this case is that we have a whole set of different types of models that are being built by object interactions, so pairwise object interactions, and different lengths of history. So for some of these types of object dynamics, you have to be not one step mark off, but you have to remember quite a long history in order to predict the effect of your actions. So in particular, for something like jumping on crocodile heads, turns out you have to wait for very precise timing in order to model how the crocodiles open and close their mouths. So we had to think about both sort of what was the right Markovian assumption, what n-step Markov, and what were this, we used a decision tree representation to represent the potential object dynamics. And then given all these classes of models, then we pick the one whose entropy is essentially lower than a threshold. So something that looks basically deterministic. And we pick the simplest model that is deterministic. So that allows us to learn different sorts of dynamics models like this, like what happens when you have sort of quicksand pits that open and close. It allows us to do things like this, like jump over crocodile heads, where you need very precise timing. And so it takes quite a lot of data to learn this, because you do have to have this, quite long history. And things like this, where you want to be able to swing with a rope over a lake. So that was the first idea. The second has to do with planning. So if we go back to thinking about what I was saying before of this sort of tabular optimism under uncertainty, I argued that the second step was just doing MDP planning to compute a value function. But the thing that I didn't really emphasize here is that it's MDP planning which is perfect. So the idea is that, in tabular settings, particularly small tabular settings, it's possible to do perfect planning. You just solve for the value function that includes your reward bonus, and then you can use it. But in this object representation, even though it's more compact than the pixel representation, it's still very large. There are a lot of objects, we're representing their bounding boxes, and so doing computational planning on this representation is still really challenging. So one of the things that we investigated, this work is under submission, but one of the other things we looked at here is what type of exploration strategies are helpful when you're going to be doing approximate planning, and how does that approximate planning intersect with the exploration strategies? So what we found in this case is that being optimistic, rather than doing something like Thompson sampling or doing Bayes adaptive approaches, was much better. And my conjecture for this is that often Thompson sampling is efficient because parts of the world that you sample look optimistic. But if you're doing approximate planning, you may not consider reaching those places, and so it's more likely that the value function you compute will not be optimistic. There's some similarly interesting issues of why Bayes adaptive approaches don't do as well here. But optimism, where you're sort of adding a reward bonus to everywhere. And our reward bonuses here look very similar to kind of these type of reward bonuses that you see in other optimism papers, where you're essentially having a bonus for visiting states of the world you haven't visited before, which in our case are represented by objects. So what this allows us to do is to explore more and explore faster. So by combining these ideas, if you look at our approach, on average, we would be visiting this set of rooms compared to that of DDQN with eGreedy, which is close to state of the art, but a lot of the other deep RL approaches have very similar performance. Now, just to keep in mind here, we're definitely not done. Remember, there's 255 rooms here. So this is only a subset of that 255 rooms. So there's still a lot more work to be done. But if we look at this, we're still making significant progress. So DDQM with eGreedy on average visits 6 rooms in 2,000 episodes, whereas our approach on average visits 17 rooms in 50 episodes. So we're just being much, much faster at being able to explore the world. And this is important because the reward is really sparse. And so this allowed us to obtain, to our knowledge, the first positive success on Pitfall without human demonstrations. So what am I showing you here? I'm showing you that we did 100 runs of our algorithm. For each run, it went for 50 episodes. And what we looked at is sort of the best episode score during those runs. So in each of those 50 episodes, what's the best score it got? And what you can see here is that some of the time we're getting to room -17, where you can start to get over 1,000 reward, and some of the time we're getting to room 7, where you get over 3,000 reward. So we are able to explore efficiently enough that we can start to uncover these positive rewards and learn different policies than just kind of cowering in place. Now again, full disclosure, look at that bar on the left. There's still a lot of the time where we don't reach this. So there's still a lot of work to be done in these cases. But I think it's really encouraging that it is possible to explore fast enough, even without having a teacher show you what to do in these types of domains. And again, we have existence proofs of that. People can do this task even if someone doesn't teach them how to do it. So this is, a run of our algorithm, one of the episodes, and you can see it, our agent learns to jump over these rolling logs, and you can see the scorpion underneath, and it has to learn models of how the scorpion works, how to be able to jump over the crocodiles, and eventually it will reach a place where after getting through, and again swinging, and remember, because it's sharing information across objects, if it can encounter the same object, it knows what to do, and eventually it gets to the gold here and can get high reward. So this is work that's in submission. I think there's a lot of really interesting extensions. One thing that I think is critical is that we don't have memory right now outside of the way that we're learning our object models, in the sense that we're not building an explicit value function to use at the leaves of how we're doing planning, which is Monte Carlo tree search. And so an ongoing work right now is to combine our sort of forward search method for planning with a value function that leaves, so that it can remember its experience and transport that across time. But just to summarize, I think that being able to do well in high stakes, expensive domains is really important for many of the applications that RL could really benefit, particularly those involving people. And I think model-based reinforcement learning can be really helpful for that. And I've discussed a number of different ways that we can think about how do we evaluate the performance of those algorithms, as well as how we can do more efficient exploration given those. Thanks.
You show this really nice result that you can get these problem-dependent, that the UBEV algorithm has this nice problem-dependent ability to take advantage of the problem-dependent structure. So what actually did you show that it was able to take advantage of? Like, what domain structure was it actually taking advantage of?
That's a great question. So the question was saying, like, what type of domain structure? So in the paper that we just had this week, we were looking at when the MDP was really abandoned, which means that your actions do not affect the next state distribution. Your state distribution is always being sampled from a stationary distribution. And so in that case, if your world is really abandoned, we can get bounds that match basically the best higher order terms for bandit algorithms, even though your algorithm is treating it as if it's solving this H-step MDP.
Okay, so as a follow-up question then, so when you designed the algorithm, you weren't designing it to take advantage of this property. So how did it just happen that it's taking advantage of this?
That's a great question. So why does this occur? So we were surprised too. I think what happens in this case is that essentially the domain is really fast mixing. It mixes incredibly quickly, and because of that, your value function converges really, really quickly towards the optimal value function. And so it's because of that structure that we can show in the analysis that your main dependence is as if you knew it was a bandit, even though you didn't.
Hi, thanks for the talk. One of the, if I understand right, the reason why expected regret isn't a good objective is because sometimes you might get really bad outcomes. Why don't you just change the definition of reward to reflect what you're actually trying to optimize?
Why don't you just reflect the... You mean if there's, so I think what you're saying, Ian, is that you're saying, like, well, what if there's sort of constraints, or what if there's other things which mean those are completely intolerable, some of those outcomes, and so can you just put that information into the reward function?
Right.
I think in some cases that might be possible, but in other cases I think it's tricky to do. And I think one of the nice things of Epsilon Pack is it tells you sort of how many of different levels of mistakes you might make. And you can imagine using this to compare across different types of policies, or for this particular setting, how much data are you willing to collect in order to sort of suffer different costs. Whereas I think that the expected regret, you again sort of put more emphasis on the domain designer to really get that reward structure correct, so that when you optimize it, it's going to be balanced. Because I think when you specify the local rewards, it's not always clear how that will affect the cumulative.
One last question.
Thanks for the talk, Emma. So you made a comparison in the pitfall results of, I don't know, double DQN, I guess, visiting 6 screens over 2,000 episodes, while the other algorithm was visiting 17 over 50 or something like that. And the question is, if I understood correctly, you kind of start with a lot of additional information, right? Like the objects and so on. And how much do you think I mean, because clearly epsilon greedy, we all agree it's not going to be the one doing pitfall. But how much do you think that this data efficiency of these algorithms is because they're trying to learn a representation from scratch without assumptions of Markovian or macro actions? And how much do you think it's actually because of exploration itself?
I think it's a great question. I think a lot of it's because of exploration. In this particular case, I will double check after this, but I'm 99% sure that the DDQN was done on the object representation. So we were given the object representation to DDQN, which may or may not be a good thing because the object representations going directly model free have not always shown to be as effective. But I think that something like some of the nice work with like Mark Bellemere on count-based exploration has had similar performance. And I think it's because those are not directly incentivizing building a model and directing your exploration for learning that and then being able to share that across. So I think even if you're using object representations, if you're not learning the model of that and the dynamics model, this is a place where I think being model free has a significant limitation.
Let's thank Emma one more time.